Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics-2. In this lecture, we will discuss about the power series solution about an ordinary point. In the last lecture, we studied about ordinary, singular, regular singular and irregular singular points. First, we recall the ordinary and singular point here p2x d square y by dx square plus p1x dy by dx plus p0y equal to 0 be a second order homogeneous linear differential equation where p2x, p1x and p0x are functions of x with p2x not equal to 0. So we divide whole equation by p2x. Then we get d square y by dx square plus p1 by p2 dy by dx plus p0 by p2x dy y equal to 0. Now we take p1 by p2 equal to px and p0x by p2x equal to qx. Therefore, our differential equation is d square y by dx square plus px dy by dx plus qxy equal to 0. Now, a point x0 is said to be an ordinary point of differential equation number 2 if limit of px and limit of qx both are exist at x0. Then it is known as ordinary point of our differential equation number 2. If one of the limit x tends to x0 px or limit x tends to x0 qx or both does not exist at x0, then it is known as singular point. Now we will see the power series solution about an ordinary point. Let x0 be an ordinary point of second order homogeneous linear differential equation p2x y double dash plus p1x y dash plus p0x y equal to 0, where p2, p1 and p0 are functions of x with p2x not equal to 0. Here y double dash is a second derivative of y with respect to x, that means d square y by dx square, and y dash is dy by dx. Now we find the power series solution of our differential equation about an ordinary point is like y equal to sigma n equal to 0 to infinity a n x raised to n, that can be written as a0 plus a1 x minus x0 plus a2 x minus x0 square up to so on, and nth term of this series will be an x minus x0 raised to n up to so on. Now first we differentiate this series with respect to x, and our differential equation is second order differential equation, so we again differentiate second time it. Then first of all y dash equal to sigma n equal to 1 to infinity n x minus x0 raised to n minus 1. Here we are starting the series from n equal to 1 because if we take the n equal to 0, then first term will be 0 in this series. So this is our y dash, which is n equal to 1 to infinity n x raised to n minus 1. Similarly, our y double dash is starting from n equal to 2, so it is sigma n equal to 2 to infinity n minus 1 an x minus x0 raised to n minus 2. If we can start this series y double dash from 0, then first two term will be 0. Now we put y dash and y double dash in our differential equation number 1, and we find the coefficient a2, a3 up to so on an in terms of a0 and an when a0 and an are not equal to 0. Now let us see by some example. Here our example is x square plus 1 y double dash minus x y dash plus 2y equal to 0. Here our coefficient of y double dash is x square plus 1, which is never 0 for any real number. Therefore we can say that all the real numbers are ordinary point. Here we will find the solution about x equal to 0. Here we can see that x equal to 0 be an ordinary point of the differential equation. Now our power series solution is y equal to sigma n equal to 0 to infinity an x minus x0 raised to n, where x0 is 0. that can be written as y equal to a0 plus a1 x minus x0 plus a2 x minus x0 square plus a3 x minus x0 cube up to so on. Now we will put the x0 equal to 0 in our series, then finally we get y equal to sigma n equal to 0 to infinity a n x raised to n. Now we differentiate this series with respect to x, then we get n equal sigma n equal to 1 to infinity n a n x raised to n minus 1. Here this series can be start from n equal to 0, but first term will be 0. So here y dash is starting from n equal to 1 to infinity n a n x raised to n minus 1. Similarly, y double dash is sigma n equal to 2 to infinity n minus 1 a n x raised to n minus 2. Now put y dash y double dash in our differential equation, x square plus 1 y double dash minus x y dash plus 2y equal to 0. Then finally we get x square plus 1 into sigma n equal to 2 to infinity n minus 1 a n x raised to n minus 2 minus x sigma n equal to 1 to infinity n a n x raised to n minus 1 plus 2 times sigma n equal to 0 to infinity a n x raised to n equal to 0. Here we will put the each summation y dash and y double dash in our differential equation in place of y dash and y double dash. Now we will find the recurrence relation to convert a2, a3 up to so on in terms of a0 and a1. Let us see how to find the recurrence relation in power series solution. Here first of all our differential equation is this, and it can be rewritten as x square y double dash plus y double dash minus x y dash plus 2y equal to 0. Now we put the summation in this differential equation y double dash, then x square sigma n equal to 2 to infinity n minus 1 an x raised to n minus 2 plus sigma n equal to 1 to 2 to infinity n minus 1 an x raised to n minus 2 plus minus x sigma n equal to 1 to infinity n x raised to n minus 1. This is the value of y dash in summation form, and last form is 2 in plus 2 n 2 times n equal to 0 to infinity an x raised to n equal to 0. Now we multiply each coefficient inside the summation, then sigma n equal to 2 to infinity n minus 1 an x raised to n. Second summation is as it is, sigma n equal to 2 to infinity n minus 1 an x raised to n minus 2 plus sigma n equal to 1 to infinity minus n x raised to n, and last one is sigma n equal to 0 to infinity 2 an x raised to n equal to 0. Now we have all the summation have a x raised to n power, and in this summation we have a x power is n minus 2. We convert into n power to replace n by n plus 2 in the second number summation. Therefore, we have a sigma for summation is as it is, n equal to n to infinity n minus 1 an x raised to n Now here we replace then by n equal to n plus 2. We have a n equal to 0 to infinity n plus 2 into n plus 1 an plus 2 into x raised to n plus sigma n equal to 1 to infinity minus n x raised to n plus sigma n equal to 0 to infinity 2 an x raised to n. Now we have a x raised to n power in each summation, and we first write down the coefficients of n equal to 0. So n equal to 0 in these two summation, and we get 2a2 plus 2a0 into x raised to 0 plus, now we are putting the n equal to 1 in these three summation. First one is second summation, third summation, and last summation. Then we get plus 6a3 minus a1 from the third number summation plus 2a1 from the last summation into x. Now we can take the common sigma x raised to n common, n equal to starting from 2 to infinity, and we are taking the x raised to n common from all summation. Then we get n into n minus 1 an plus n plus 2 into n plus 1 an plus 2 minus, now we have a minus n plus, from the last summation we have a 2an and x raised to n common equal to 0. So that is our final summation form of our differential equation. And comparing coefficients of x0, x and x raised to n, both sides with RHS equal to 0, then we can find the recurrence relation from this step. Now we will see how to find the recurrence relation. Here for n equal to 0, 2a2 plus 2a0 equal to 0. That implies a2 equal to minus a0. For n equal to 1, 6a3 plus a1 equal to 0. That implies we have a a3 equal to minus a1 upon 6. That is our third number coefficient in terms of a1. Now for n greater than equal to 2, we have a n into n minus 1 an plus n plus 2 into n plus 1 an plus 2 plus minus n an plus 2 an equal to 0. It is coming from the last summation, and we have a n plus 2 left hand side, so we are taking the n plus 2 as a subject. Then an plus 2 equal to minus n minus 1 an plus n minus 2n upon n plus 2 into n plus 1, which is valid for n greater than equal to 2. Here n plus 2 can be written as minus n square minus 2n plus 2 into an upon n plus 2 into n plus 1, which is our recurrence relation for n greater than or equal to 2. It is coming from the last summation of n after taking the n common, which is valid for n greater than or equal to 2. It is known as recurrence relation, and from this relation we can find the further points like a4, a5, a6, a7. For n equal to 2, a4 equal to minus 2a2 upon 12. That implies a4 equal to minus a0 by 6 in place of a2. So we have a finally a4 equal to a0 by 6 because a2 equal to minus a0. For n equal to 3, we have a a5 equal to minus 5a3 upon 20. That implies we get a5 equal to minus a3 upon 4. That implies after putting the value of a3, which is minus a1 by 6, we get a5 equal to a1 by 24, which is our fifth number coefficient in the series. Here we have a a3 equal to minus a1 by 6. Now we put this coefficient in our series. Here our series is y equal to a0 plus a1x plus a2x square plus a3x cube up to so on. Here we can find the further coefficient. Here our coefficients are a2 equal to minus a0, a3 equal to minus a1 by 6, a4 equal to a0 by 6, a5 equal to a1 by 24 up to so on. We can find the remaining coefficient by recurrence relation. Here we put this coefficient in our series. Finally we get y equal to a0 plus a1x plus minus a0x square plus minus a1 by 6 x cube plus a0 by 6 x raised to 4 plus a1 by 24 x raised to 5 up to so on. Now we will take the a0 common from this series. We can get y equal to a0 into 1 minus x square plus x raised to 4 by 6 up to so on, and after taking the a1 common, then we get a1 into x minus x cube by 6 plus x raised to 5 by 24 up to so on. Here we get the two series 1 minus x square plus x raised to 4 by 6 up to so on. This is our first power series solution, and second one is x minus x cube by 6 plus x raised to 5 upon 20. This is our general solution y equal to c1y1 plus c2y2, where y1 equal to 1 minus x square plus 1 by 6 x raised to 4, and y2 is second power series solution x minus x cube by 6 plus x raised to 5 by 24 up to so on. Here c1 and c2 are arbitrary constant. Here we are taking the c1 equal to a0 and c2 equal to a1, which are our arbitrary constant in our differential equation. Thank you very much.